30-3s. I told you this was a short little unit at the start, and we are on to the last lesson already. So we've talked triangles, we've talked quadrilaterals, two very common shapes. Well, now we're going to kind of talk in general polygons, even though we're going to talk about regular polygons more than just polygons. And a polygon, well, just a quick refresher, a polygon refers to any straight-sided closed object. So as long as the sides are straight and it meets, it's a polygon. So there's a polygon. Now, of course, we don't necessarily look at that and think, well, that's a polygon. We think of other more specific type images in our head. But very quickly, with the polygons, a triangle, well, that's a three-sided polygon. We know that. We've done and talked triangles. Quadrilaterals, those are the four-sided polygons. Well, you then have the special names depending upon the number of sides. A pentagon, five-sided. Hexagon, 6. Heptagon, 7. Octagon, 8. Nonagon, 9. Decagon, 10. And dodecagon is actually a 12-sided polygon. Now, when you talk polygon, though, like the one I just drew, it doesn't have to be a particular kind of look to it. A pentagon, what does a pentagon need? A pentagon needs 5 sides. And there you go. 1, 2, 3, 4. It's a 5-sided pentagon. We could draw all kinds of different pentagons. 1, 2, 3, 4, 5. There's another pentagon, as long as it has 5 sides. And that's like any of these. However, a lot of times when we talk about polygons, we think of what are regular polygons. Regular polygons have congruent sides. Equal side length sides. Triangle, we've talked about it. Well, triangle, if I draw it as best I can so all the sides are congruent, there's a regular triangle. A regular quadrilateral, well, we just talked quadrilaterals. So if I have a quadrilateral, all the sides are the same, it's a regular quadrilateral, but what do we call it? We call it a square. A pentagon, now, please don't make fun of my drawings. I'm doing my best. But when we talk regular shapes, we tend to talk about the shapes. Oh, that's a little ugly. We tend to talk about the shapes, and the shapes become rounder and rounder as we add sides. So there's a regular or fairly close to a regular pentagon, and why we put the ticks. If I go to a regular octagon, well, all right, yes, you can laugh, but I think I do not a bad job. That's not a good octagon. Regular means all the sides are the same. Why is my pen not matching up? All right, maybe I can't draw a regular octagon really well, but every time you make a regular and you add sides, it tends it tends to become more circular in shape. That's what happens as you do regular octagon. I'm not even going to try to do an octagon anymore, but things become more and more round as you add sides to regular polygons. The hexagon, 6 sides. We can see that a hexagon just becomes more of a round shape than the pentagon, and the heptagon becomes rounder. You can draw them on your own if you want and make fun of mine. But not only do we get congruent sides, what we're going to talk about is we get congruent interior angles. And that's what we're going to kind of focus on a lot, is the calculations of the angles. So the angles in a square, we know, are all 90 degrees. Because to create that, if I have all the sides the same, the angles are the same. What do we know about the angles in a regular triangle? Well, that's an equilateral triangle. Each angle is 60 degrees. 60, 60, 60 is 180. And when sides are the same, angles are the same as well. And we're going to look at how to calculate those and come up with a formula for it, now that I've wasted time trying to draw an octagon. So if we take a look on page 16, this is kind of a cool way to figure out the sum. So sum meaning the total of all the interior angles in any regular polygon. What we can do with any regular polygon is pick one vertex. It doesn't matter which vertex you choose. But I want to connect that one vertex to all the other vertexes, or vertices, I guess, in this particular regular polygon. Now, what you see is when you connect one of the vertices to all the other vertices, we end up with a whole bunch of triangles. Well, here's a triangle here that has an angle, and an angle. And those three angles have a total of what? Well, they total 180 degrees, because we know the three angles in a triangle total 180. Well, I can do the same thing in this second triangle. I can look at this second triangle and say, hey, look, I have angle there, and angle there in that triangle. And those three angles all together, angle, and angle, those total 180 degrees as well. And I can do that for each of these triangles that got created by connecting the vertices. So there I have angle, here I have an angle, and here I have an angle, and those three total 180. And then the last one, well, what do I have? I have angle here, and angle here. And those three angles total 180. Well, when you take a look at that, all of these angles, when I combine them all, I've just created every angle within that hexagon. So all of these 180s together create all the total angles. So the sum of the interior angles of a hexagon, well, what do we have? We have 4 triangles, and each triangle has 180 degrees in it. So 4 180s means there's 720 degree total angles in a hexagon. It's a little proof that works for any regular polygon. If we took a look at the next page, very quickly, well, the diagram, if we have the triangle. Well, the triangle, if I start at a vertex and I join the other vertices to it, well, I end up with, there's my triangle. So how many sides? There's 3. How many triangles got created? 1 triangle. And we know all 3 of those angles are 180 degrees. So try the pentagon and the octagon that are there. See what you come up with. 5-sided pentagon. We know there's 5 sides. Well, if I choose a vertex and I connect it to all the other vertices, what do I end up with? We end up with 3 separate triangles. So we get 3 triangles, and what are the angles in each triangle? 180. So the sum of the angles would be 3 triangles times 180 degrees, and that's 540 degrees. Try the octagon and then do it with me. So we have the octagon, pick one of the vertices, and connect it to every other vertex. And when I connect one vertex to all the other vertices, what do we end up with? We end up with a whole bunch of triangles. And again, all the angles in these triangles, all the angles in the individual triangles really are the total. So we end up with an 8-sided octagon. We have 1, 2, 3, 4, 5, 6 triangles. So the sum of the angles would be the 6 triangles times 180 degrees each, which is 1,080 degrees for all of the angles in an octagon. Well, when you take a look at that chart, do you see a pattern about how to calculate the sum of the angles? Well, a triangle was really one triangle times 180 degrees. So one triangle times the 180. The pentagon was 3 triangles times 180. The octagon was 6 triangles times 180. So the question is, do you see a pattern? We have to multiply by 180 degrees, but what do we multiply? Well, look at this. Where does this 1 come from? The 3, the 6, a pattern's developing. 3 sides in a triangle makes 1 triangle. 5 sides in a pentagon makes 3 triangles. 8 sides in an octagon makes 6 triangles. So we want to take the number of sides, 3, 5, and 8, but what did I do every time to get the number of triangles? We subtracted 2. So there's the pattern that's occurring. 3 sides makes 1 triangle. 3 minus 2 is 1. 5 sides in our pentagon means we created 3 triangles. Subtract 2 to get 3. Our 8-sided octagon, which you can see better drawn there than what I was trying, subtract 2 gave us 6 triangles. So there's what we need to use for a formula on page 18 for the sum of the angles in a polygon. 180 degrees times n minus 2, where n is the number of sides. So on this chart, you see the big chart there. Well, we just did the octagon. So let's take a look at the octagon again. What did we see? There were 8 sides. So what does our formula tell us to do? 180 degrees times, but how many triangles were there in the octagon? Well, if we go back, the octagon had 6 triangles. So what we need to do is 180 times 8 sides in an octagon, subtract 2, which tells us 180 times 6, which was the 1080 degrees that we got on the other page. So that formula works. A heptagon has 7 sides. So a heptagon, what's the sum of all the angles in a heptagon? Well, the sum of the angles will equal 180 degrees times 7 sides, but take away 2 because it would make 5 triangles. So 180 times 5 is 900 degrees is the angles in a heptagon. Nonagon, 9 sides. So the sum of the angles, 180 times 9 sides, subtract 2, which gives us 7 triangles. 180 degrees for 7 triangles leaves us with 1,260 degrees, all the angles in a nonagon. And a dodecagon, which has 12 sides, 180 degrees times 12 sides less 2. Because a 12-sided dodecagon, if I went through that process, would create 10 triangles. 180 times 10 triangles is 1,800 degrees is the sum of the angles. A nice, simple little formula for dealing with the sum of all the angles in a polygon. So on page 18, problem number 1. Read it, and then give it a try and come back and I'll walk through it. So if you had a house and it was an octagon, you want the sum of the interior angles. The sum of the angles would be 180 degrees times 8 sides in an octagon less 2 180 degrees times 6 works out to be 1,080 degrees is the sum of the angles. If you had this octagon for a house and every side, I'm not going to try to draw it entirely. Look at this. Hey, that one's not bad. That one wasn't bad. If every side was the same and was 10 feet, what would be the perimeter? The perimeter would be 10 feet times 8 sides. You'd have 80 feet of wall in that particular room. Problem number 2, a little bit different. This time it gives us the sum. It's saying there's 2,340 degrees in a polygon. How many sides on the polygon? Well, this time I'm just going to write the formula first. The sum of the angles is 180 times n minus 2. Well, we know that the sum is 2,340, so now that will equal 180 times n minus 2. We need to figure out what n is. I could first divide by 180. Because 180 is being multiplied, we divide by it on both sides, and we would be left with 13 equals, and we still have the n minus 2 over there. Add 2 to both sides to get n by itself, and it would be a 15-sided polygon that has an interior sum of angles of 2,340. Working backwards. Looks tricky, but it's manageable. So this little formula is nice for calculating the sum of all the angles in any polygon. Now the second step to this is on page 19, which says, what's the sum of each interior angle? Or I guess, what's the total of each interior angle? So we don't want to know what the total is. We just want to know because every angle is the same size. We just talked about regular polygons all having the same sized angle. So that's what we're looking at right now. But how big is each? Well, this isn't a big stretch because they're congruent angles. And we already talked about, if I can get the sum of all the angles, the sum of all the angles is equal to 180 times, we took a look at this, 6 sides minus the 2, that works out to be 720 degrees. But if I want to know each individual angle, what's great? They're congruent. So if I know that these all together total 720, how do I find each one? Divide by the 6 angles. And it should divide even because they're the congruent. That's the whole key. So 720 divided by 6, that leaves us with 7, and this wasn't, this wasn't in the book, but I was just talking about it from earlier. 720 divided by 6, which I got to do the math, 120 degrees each angle. And there you go. So this isn't a big stretch. It's basically using the one calculation we know, but then we just have to figure out, well, how many triangles or how many angles do we have? And that's what we're going to divide by. So there's your new equation. The sum of each angle will be the sum of all the angles, but now we divide it by how many angles there are. Because the number of angles is equal to the number of sides. 6 sides means there's 6 angles. So that n, even though it represents the number of sides, well, it's the same as the number of angles. Find all of the angle size and divide by the number of angles. That's what we're going to do. So problem number 2 on page 19. Shelby's building her mom a special wall clock. She wants to make it in the shape of a regular dodecagon. What is the measure of each angle? So here's the dodecagon clock. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides, dodecagon, which means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 angles. Well, let's first, to get the angle size, let's get the sum of all the angles, which in this case, number of sides we know is 12. That's going to find the total angle, but we know we're going to divide that equally by 12 angles. So 180 times n minus 2 divided by n, and that's what we have. 180 times 12 minus 2 is 10, is 1,800. Divide that by 12, and we get 150 degrees is the size of each angle in a dodecagon. That's a 150 degree angle. That's a 150 degree angle. That's a 150 degree angle, and so on, and so on, and so on. Not a difficult calculation if you're attentive to it. Page 20, problem 3. The floor of a gazebo has the shape of a regular octagon. What's the measure of each interior angle? So I've used the program, notebook software, to draw my octagon. So there's our octagon. We want the measure of each interior angle. Well, there's our formula. Each angle will equal 180 times n. Well, it's an octagon, so there's 8 sides. Subtract 2, but then we're going to want to divide that by the 8 sides. So 180 times 6 to get the total for an octagon, which is 1,080. But we need to divide that by 8 now, because that total sum of the angles split evenly amongst 8 angles is 135 degrees for each angle. So there you go. We have a 135 degree angle everywhere. But what's nice with a regular polygon, any regular polygon, like part B says, can be split into congruent triangles. Every triangle is the same. Because it's a regular polygon, every base is the same, and it meets in the middle, so all the measures are the same. So we now have a triangle that basically has been taken from that octagon. There's our new triangle. Well, what do we know about this? Because there's where we divided it, but now we have these shapes. What are the interior angles of the congruent triangles? Well, this angle here, which matches up here, I took it out. I don't know if this will work. I could take it out. It's going to stay together, unfortunately. But I could take that one and put it on top. Well, what we hopefully see is that this here is half of the 135 degrees. So this part here is just half of the entire 135. So we have an angle here, 135 divided by 2, because it's half of that angle size. And 135 divided by 2 leaves us with 67.5 degrees. Well, what's important here? One more thing about these triangles. These triangles that get made, the distance from the middle to a vertex and the middle to the other vertex, well, those are the same distances. We have an isosceles triangle. Now, the bottom might not be the same, but those two sides are the same. And when you have an isosceles triangle, you have two sides that are the same, which means the two angles across from those sides are also the same, which was part of our isosceles triangle characteristics we talked about a couple lessons ago. And now what do? Well, we know a triangle is 180 degrees total. If we take away the two angle sizes we know, we end up with a 45 degree angle. So we have 45 degrees and 2 times 67.5 degrees in that triangle. So once you have a shape and a little bit of knowledge, man, shapes are all related. You can get all kinds of information from it. And finally on page 20 to finish off, well, here problem 4 says, each angle of a regular polygon has a measure of 162 degrees. So we know the angle is 162 degrees. How many sides does the polygon have? Well, we know the sum of each angle is 162. So let's plug into our formula. 162 is equal to 180 times n minus 2 over n. Because at this point, we don't know what n is. Well, this is a pretty tough math question. I'll be honest with you. What I would do with this question is I would cross multiply. I can put 162 over 1, and we've done some cross multiplying. So we're going to multiply, and this goes back to our math 10 even algebra skills. I'm going to cross multiply, so 1 times 180 times n minus 2. If I multiply 1 by that, I just get it. 1 times anything is just that anything. But I also have 162 times n. And remember, when we cross multiply, these have to be the same thing. So they're equal to each other. So this equals 162n. Well, from there, a little bit of math. We need to multiply to get rid of brackets. 180n minus 360 equals 162n. What can we do? Subtract 180n so that it gets paired up with the other 180n on the other side. We have negative 360 is equal to negative 18. And when we divide, n, divide by negative 18, we get n equal to 20. So it's a 20-sided polygon. That's a tough question. I wouldn't stress too much about it, but it's kind of good to see that when you have a formula, we can plug in and solve. You have pages 21 and 22 to do using these two formulas. Two formulas similar, but different enough you're going to have to think. Have fun with it, and then close to getting the assessment. Have a great day.